Okay, in this video, we're going to be discussing our final two exponent rules and then also sort of an exponent rule, but really a definition of exponents as well too, or two definitions, I should say, using exponents. And that will wrap up our work with exponent rules. We are going to be finishing up these skills on Wednesday and a quiz on Friday. So I know I said this in class, but please note that. All right, so let's take a look. We have done power of a product, product of a power, and then power of a power. Here we're going to be learning dividing powers, okay? How are we going to take terms that use exponents and then divide them, all right? So let's take a look exactly what's happening here. We have a to the fifth divided by a to the third power. And let me just get my pen ready. So what is really a to the fifth in the numerator? Let's take a look. That is, of course, a times a times a times a times a, right? And what's a to the third? That's a times a times a. Okay. Now, when we cancel out a's, meaning what is this really? This is that we're finding common factors between a and a, which is a. So a divided by a is 1. A divided by a is 1. So anything that has an a in the numerator or denominator will cancel. So this is a and a, a and a, a and a. So what's left? A times a, okay? Which is equivalent to a squared, which, as you'll see, the exponent rule sort of developing, is a to the 5 minus 3. What are the two exponents we had here? 5 minus 3, 2. All right, so let's take a look at that more clearly, and we'll sort of define it. All right, so let a be a non-zero real number and m be positive integers such that m is greater than n. If that's the case, then we can say this in words. To divide powers having the same base, you subtract exponents. Okay? 5 minus 3, we just did that. We're subtracting. What is the algebraic representation of that? A to the m divided by a to the n is a to the m minus n. And of course, a cannot be equal to 0. So an example of that, let's take a look. Maybe let's say something like this. R to the fifth power divided by r to the fourth power. What's that? Well, that's simply r to the 5 minus 4, or r to the first, which is, of course, equivalent to r. Okay, let's take a look at some more examples. We'll just do a couple here, just so you can see how this develops. This is, of course, pretty easy to identify, but let's say y to the 20th, okay, divided by y to the 10th. What's that? Well, that's simply just y to the 20 minus 10, which is equivalent to y to the 10th. Another one. Let's use a real numbered base this time. So let's say 2 to the 7th power divided by 2 to the 3rd power. Well, what's that? That's 2 to the 7 minus 3, or to the 4th power. And we can just leave it as 2 to the 4th in this case. All right. Let's take a look. Okay, so first of all, I want, of course, you guys to do the your term problems. Note this. When I say b to the 5th divided by b, what is b in terms of an exponent? Well, that's just b to the 1st. So use that. I gave you a small hint there, but use that in your calculation. Okay, now we are raising a quotient to a power, meaning that I'm raising a fraction. A quotient is really just a fraction. It's a divided by b, but this is when you raise a fraction to a power outside of parentheses. So a over b raised to the 4th power. So let's take a look exactly what that looks like. Okay, so what is really a over b raised to the 4th power? Well, anything that's raised to a power is just something times itself. So that means a over b times a over b, okay, 4 times. So this a over b, for the fraction a over b, times itself 4 times. We know that because these are all under the same denominator here, or this, sorry, because this is multiplication, we are safe to say that we can call this a times a times a times a, and b times b times b times b, right? Because all we're really doing is just, when we multiply fractions, is just multiplying numerators and multiplying denominators. So what are the multiplication in terms of exponents? So how can I represent this expanded form in terms of exponents? Well, that's just simply a to the 4th power. Same thing with b to the 4th power. Okay? So let's take a look at this in rule form. So if a and b are real numbers, and that b is not equal to 0, and m is a positive integer, then we can say this. We can say To find a power of a quotient, you just find the power of the numerator and the power of the denominator and divide. Now, you would divide if you can, simplify if necessary, but basically what it means is that, and this is the algebraic representation, if I have a over b and I raise it to the m power, I'm just raising both a and b individually to m. So raising the numerator to m, raising the denominator to m. So an example here would be, let's say something like, if I have x over y and I am squaring x over y, well, that's just simply raising x to the square and then y squared. Okay, something to that effect. And let's look at some more examples here. I'll draw out a few. So let's say maybe we have m over n, and we are raising that to the 7th power. Well, that's just m to the 7th, n to the 7th. Okay, let's look at another one. How about q over r to the 5th power? Well, that's just simply q to the 5th over r to the 5th. So hopefully you're seeing this now. This one is relatively easy to see. All you're really doing is just representing the numerator and denominator by individually raising them to whatever power the fraction is being raised to. Okay? So we'll see this using simplification in a bit, but I just want you to try some of your problems, some problems here on your own. X over y to the 4th, p over q to the 8th. Okay, 0 and negative exponents. So let's take a look at a pattern here. I think this is easily seen in a pattern form. 2 to the 4th power, that's 2 times 2 times 2 times 2 is 16. To the 3rd, 2 times 2 times 2 is 8. 2 squared, that is 4. To the 1st power is 1. And what's the pattern that's developing here? Clearly, these aren't subtracting one individual number, right? Because between 16 and 8, I'm subtracting 8. Between 8 and 4, I'm subtracting 4, etc. So what is really going on here? This is not a common number that I'm subtracting. This is called a common ratio, okay? So what does that mean? That means that I'm not just subtracting, a linear amount from each number. No, the pattern here is a ratio, meaning that I am dividing by a certain number. So how do I get from 16 to 8? I divide by 2. How do I get from 8 to 4? I divide by 2. How do I get from 4 to 2? I divide by 2, and so on and so forth. So it would make logical sense to see that if I'm going to this number here, I'm also dividing by 2. Well, what's 2 divided by 2? That is 1. Okay? What is 1 divided by 2? That's 1/2. What's 1/2 divided by 2? And I'll do that work over here just so you can see. What's 1/2 divided by 2? Well, that's the same as 1/2 times 1 over 2, because I'm multiplying by the reciprocal is 1 over 4. So this is 1/4, right? And note that this is still intact, this pattern, divide by 2, divide by 2. So as I go down in my exponents, meaning that I'm decreasing my exponents by 1, from 4 to 3 to 2 to 1 to 0, etc., I'm still just dividing by 2. 16, 8, 4, 2, 1, 1/2, 1/4. And the pattern would continue if you went to 2 to the negative 3 and so on. So let's take a look at some of these are really definitions of exponents that this develops. Okay, so a to the 0 power is 1. So what does that look like algebraically? Anything raised to the 0 power is 1, okay? You could literally tell me any variable, any number, as long as it is real valued, okay? Then for sure, that answer is 1. So this example here is fairly easy to define in that all I'm literally just picking anything. I'm going to say 247 raised to the 0 power. That's 1. So literally anything I choose is 1. Okay. Let's take a look at another one. And a to the negative n is basically just the reciprocal of a to the n. So what does that mean? That means that a to the negative n is equal to 1 over a to the n. All right, so let's take a look at that in terms of an example. And that is what we saw with the negative powers of 2 in the previous example. So let's take a look here. So anything that I raise to a negative power, let's say p to the negative 3 power, well, that's just 1 over p to the 3rd power, because 3 is n here, so p to the negative 3 or negative n is 1 over p to the third, etc. So all I'm doing when I'm taking something and raising it to a negative exponent is if it is in the numerator, I am dropping it down to the denominator, okay? So anything that's being raised to a negative power, whether it's a single variable or something within parentheses, it drops down to the denominator. That's how you can think about it. Okay, last one, in that this one defines something that's negative exponent in the denominator kicking up to the numerator. So if I have a to the n, all right, that's a reciprocal of a to the negative n, meaning that if I have a positive valued exponent, that's equivalent to 1 over that same base raised to that negative n. So let's take a look at what this means here. If I were to raise, let's see, if I were to say, okay, well, let's deal with the negative side first, actually. So maybe 1 over q to the negative 5 power. That's just equivalent to q to the 5th, right? Something to that effect. Okay, so what did I do here? I have a negative exponent in the denominator. I bumped it up to the numerator, okay? So let's do a couple of practice problems here. Okay, so 0 is relatively easy. Even if it's a variable, I had 247, I think it was before. But even a variable, doesn't matter. Even if this is unknown, this is always 1, okay? Anything raised to the 0 power is 1. Let's take a look at a negative exponent, maybe z to the negative 8th, okay? Or negative 8, I should say. So what is that? That's just 1 over z to the 8th. So I'm taking whatever is negative and I'm bumping it down. All right, same thing over here. What about, let's say, q to the 5th power? So what is that? That is 1 over q to the negative 5th. Okay, now something I want to note here, and this is a very important point and or concept in terms of negative exponents. If I have something inside of parentheses and that's raised to a negative power, everything is bumped down that's inside the parentheses. So here, I just have z that's to the negative 8th. But here, you can treat this 3x, or 3 times x, as this full sort of base that's being bumped down. So what is this equivalent to? 1 over 3x, and I'm keeping this in parentheses, so I follow my rules of exponents later. But I think a good first step is to deal with these negative exponents. Whatever is being raised to a negative exponent bumps up or down, and then we can follow the other rules of exponents we know, in that this is 3 squared times x squared is 9x squared. Okay, so I'm going to let you do some on your own here. Just to something raised to the 0 power, a negative power, and then 1 over to negative power, and tell me what these are equivalent to. Okay, so putting it all together. All right, so these next couple problems sort of put all the exponent rules we've learned together, including negative exponents, and I'm going to do a couple here and ask you to do some on your own. So first I'm going to deal with the negative exponents. As I said, I think this is really the best thing to do, is to, step 1, deal with negative exponents. So anything that is quote-unquote in the numerator gets bumped down to the denominator. So what does that mean? Now, I'm not going to deal with this negative exponent just yet. In that, I think it's easier to take, because this entire expression is in the negative 3, okay, I'm going to deal with this negative third first, okay, or negative 3 first, and bump this down. Now, in terms of my rules of exponents, I can't deal with this x to the, or I can, but actually that's not true. I can, but I think it's easier to use the rule of exponents where we raise a power to a power and take everything to the third power that's inside of here first. So what does that mean? 6 to the third power. That is, oh, jeez. I don't know what that is off the top of my head. I know that 6 times 6 is 36, so this is 6 and 3. 3 times 6 is 18 plus 3 is 21, so that's 216. All right, so this is 6 cubed is 216. X to the negative 2 power raised to the third power. Well, what is that? That's x to the negative 6, because this is negative 2 times 3. And then we have y to the third power also cubed. That is y to the 9th. Okay? So hopefully everybody followed what I did there. That was really just x. In fact, let me, just for clarity, let me actually write the intermediary step here. I'm going to write this in a second, but I want to make sure that everybody has this in a very solid way. So let's just be clear. I still have 1 in the numerator. What is this? This is 6 cubed, and then this is x to the negative 2 times 3, because this is the power to a power exponent rule that I'm dealing with, and then y to the third power times 3, right? Because this is also power to a power. So I just want to be very clear about what I did there. Okay. So let's deal with this now. This is now 1 over, we said this was 216, x to the negative 6, y to the 9th. Okay. All right. Now, my final step. A expression is not fully simplified unless all of the exponent values are positive, not negative. So are there any negative exponent values in this expression? Yes, there are. Now, to be very clear, what is being raised to a negative power? It's not 216. It's certainly not y to the 9th, but maybe that's clearer because y to the 9th is to the right of negative 6. But if 216x to the negative 6, okay, this is negative, the 216 is not to a negative power. That stays in the denominator. So this is a really common mistake that students make, in that the only thing that's bumping up, quote unquote, to the numerator is x to the 6. So the final answer here, x to the 6, 216 over 216y to the 9th. Okay, so hopefully that's clear. Another one, slightly more complicated here. Once again, first let's deal with negative exponents. I feel like that's easier to do. So what do we have here? We have y to the 4th power. This 3x to the negative 3rd is getting bumped down, so I'm not going to deal with that. So actually, no, let me put that down here now. So this is 3x to the positive 3. Okay. What about the things in the denominator? This is negative x squared, okay, y to the negative 6 power. Now, is this negative x squared a negative exponent? No, it's a positive 2, so that stays. So this is still negative x squared, okay? And then y to the negative 6, that gets bumped up. Okay, all right. So you can perform these order of operations separately in the numerator and denominator, however you choose. I'm going to simplify this numerator first, knowing that this is product of a power, or product of powers. So these add 4 and 6. So this is y to the 4 plus 6, okay? Now you don't have to write this step. I'm going to write it in here just to be clear. This is now a power of a power, so this is 3 cubed x cubed, right? And I'm still dealing with my negative x squared. So let me simplify this further, and that 4 plus 6 is 10, so that's y to the 10th. 3 cubed is 27, x cubed, and then multiply by negative x squared. Okay. Clearly I'm not fully done because I haven't combined my x's in the denominator. So my y to the 10th, that stays, right? And then I'm going to make my fraction bar, so I know that I just need to put this in the denominator. So what am I doing? I'm multiplying 27x cubed times negative x squared. First, I'm multiplying coefficients, and that this is implied that this is a coefficient of negative 1. What's 27 times negative 1? Negative 27. What about x cubed times x squared? Those add exponents, and that is x to the 5th. So my final answer, y to the 10th over negative 27y to the 5th. Okay, so these will be the hardest questions from the test, certainly, but I want you to try these. I want to see work on students' paper for this your turn. Not, oh, I didn't get it, I don't understand how to do it. At least try, you can do one step, or maybe you try it and you don't get it right. That's fine. I want you to see some writing on this paper and people to actually try on these your turn problems. That's incredibly important, especially since this is only 2 days of learning skills before the quiz before spring break. Okay, I will see everybody in class on Wednesday, and good luck.